When looking at dissolution, the K is very small. But if in the reverse direction, the K is when we're looking at precipitation, the K is very big. You know, it's 10 to the minus 10 and 4, but in the reverse, it'd be 10 to the positive 10, right? Which means that usually this amount that precipitates is pretty big. You know, it's significant change in the reverse direction, minimal change in the forward direction. And so even if you use the quadratic, what often happens is sometimes we end up with something like, you know, whatever our original amount is, 99.99999% of that original amount precipitates. If we get something like 99.99, what happens is your calculator will round that to 100% precipitation. And if we get 100% precipitation, then this goes to 0, and then we do a double check, and we're going to be off significantly. So normally, what I do here, even though intuitively this looks good because this is the amount that precipitates, but because of the math involved and because of the risk of calculator round-off error, I don't leave it like this. What I do is I just reset it here. And so alternatively, we can reset this. If we reset this, then I'll have my silver chloride solid. This goes to silver ions, this chloride ions. And my original initial conditions are 0.0999 molar and I'll just write this 599 molar. Okay, then we reset it by shifting this 100% to the left. We reset to the favored side. And so in this particular chapter, for KSPs, we reset it to the left because KSPs in general are very small numbers. And so that means the reactants are favored. KSPs we reset to the left, but for KFs are typically very big numbers. And so we reset those to the right. And so in this chapter, we'll be resetting to the left or resetting to the right, depending on if we're dealing with a KSP or a KF. We'll see KFs later. And so what I'm going to do is I'm going to reset this to the left. So I got to look. I'm going to have 100% reverse reaction. So what's the limiting reagent going backwards? Limiting reagent would be chloride. And that means I'm going to have some silver remaining. Do you see that? And so I got rid of all the chloride. That's 0.0599. That means I'm going to lose 0.0599 worth of silver because of 1-to-1 mole ratio. So this would be the reset. When I reset this, then this is looking at the problem a little differently. We'll get the same answer, you know, assuming that the calculation is correct. But after I reset it, now what's going to happen? Well, now we're thinking about this problem as being a common ion. That is, I have a bunch of silver ion in here. How much silver chloride will dissolve? And so when I'm looking at how much silver chloride will dissolve, then that's S. S is the maximum amount of silver chloride that dissolves. So this is going to be plus S molar plus S molar. And so at equilibrium, I'm getting a 0.0940 plus S molar and S molar. And so here we know this. There are two reasons why the simplifying assumption will fail in this particular setup. One, if we assume X is small, then X drops out as a variable and we can't solve for X, right? And two, X in the reverse direction should be huge because the reactants are highly favored over the product. Over here, by resetting this, and we look, the KSP is very small, so we don't expect this to be very soluble. I mean, the KSP is 10 to the minus 10, and so S should be very small. We don't expect much. And so here, the simplifying assumption is likely to work. And 2, S doesn't drop out because we have a 0 here. The more zeros we have in the initial, the easier the math is. Okay, and the other reason was your calculator. Here, your calculator might round off. It depends on the scenario because it might not, round off to 100%. Depending on what that change is. But here the change is very small, so it's not going to round it off. You can just do it in scientific notation. So let's go ahead and do the calculation here. The complicated thing is that the way we look at the S is different. Here this is the amount that dissolves in the presence of the common ion, silver in this case. Silver being the excess. And so let's go ahead and solve this. We'll just use the simplifying assumption. It's going to be 0.00940 times S, which means that S is equal to what? Well, it's going to be 1.8 times 10 to the minus 10 divided by 0.0094. 1.8 times 10 to the negative 1.91 times 10 to the negative 8. Is the simplifying assumption valid? If we add, 1.9 times 10 to the negative 8 to this, is it really going to change much? This is 10 to the negative 2, that's 10 to the negative 8. It's not going to have any impact on this. Barely. Then over here, the chloride's going to be 1.91 times 10 to the minus 8. And then we double check it. Does K work out? Well, let's take a look. It's going to be about 2 times 9 is about 18. Yeah, it works out. This looks good. Okay, it works out. So the question comes up, how much was precipitated? Uh-huh. Oh, shoot. Yeah, you're right. It's going to change this to 10 to the negative 9. All right, 10 to the negative 9. Okay, now the K should check out. All right, to figure out how much precipitated, over here, if we didn't reset, it'd be easy. The amount that precipitated, the percent that precipitates, X is the amount that precipitates. And this is the original. So the percent precipitation over here would be easy. Percent precipitation is just going to equal whatever our X came out to over the original, 0.90999 times 100%. That would be the percent precipitation here. But if we reset it, what is the percent precipitation? Because now we aren't dealing with X, the amount that precipitates. Now we're dealing with S, the amount that dissolves in the presence of this common ion. It's the exact same problem. We should get the exact same equilibrium concentrations, but the calculation is more convoluted over here because we reset it. And so because we reset it, we have to calculate this. First, we have to calculate the percent silver remaining unprecipitated. And so in order to do that, we have to determine what the silver ion concentration. Actually, let's do it here. Okay, the percent silver remaining unprecipitated is going to equal the amount of silver at equilibrium. This is going to be the amount of silver at equilibrium, 0.0940 molar at equilibrium, versus the original amount, The original amount is 0.0999 molar. This is before resetting times 100%. So what does that come out to here?
94.094.
Okay, about 94% remaining. Therefore, the percent silver precipitated would be 100% minus this, which is going to give us 5.91% precipitation. So by adding that drop of HCl, we only precipitated about 6% of our silver ion. Right? So I'm going to need a lot more drops of HCl to precipitate it out. Okay. Well, a challenging question might be, how many drops of 6.0 molar HCl are required for, what did we call complete precipitation? Yeah, real complete precipitation is going to be impossible because we can't add enough. But for practical purposes, we're going to say that 99.9% precipitation is complete. So quote complete, unquote precipitation. How many drops? So how would you tackle a problem like this? Well, thinking back to the titration calculations, you had two types of calculations. You had your standard calculation where you're given the volumes, you mixed it, you did step I, and then step 1, etc. Right? And so you started from the beginning and then you worked to the end. The end being the pH, let's say. But you also had calculations where you're given the pH and then you'd have to work backwards to go to the beginning, right? And so this would be an example of a calculation where we're given the end result. We want 99.9% precipitation. We just have to work backwards to figure out what we had at the beginning. In order to do that, we just set up the whole calculation and see how we can figure it out. And so we're starting off with 50.0 milliliters, 0.100 molar silver ions in solution. And then we're going to add some 6.0 molar HCl. But how much HCl do we need to add in order to get 99.9% precipitation? That we don't know, right? And so we're going to call it plus, I'd like to call it plus maybe drops, Z drops, but it's a hassle with the units. So we want to keep the units the same. So let's call it plus Z milliliters. And then convert milliliters to drops once we figure out how many milliliters that is. And so this is our unknown. Our unknown's right at the beginning. And so let's just set it up like we set up the others. What's the first thing we need to do from here?
Reset.
We're not going to reset. We're going to Yeah, dilute, solution dilution, right? And so we need to figure out the new concentration of HCl. Call this the initial. That's going to be Z over 50.0 plus Z times 6.0 molar. And this is the same as the chloride ion concentration initial. And then the silver ion concentration is going to be a 50.0 to 50.0 plus Z dilution of 0.100 molar. We don't know what Z is, but gotta get the rest of this. Okay, after we do the solution dilution, this gives us our initial concentrations before reaction. Then we allow it to react. No matter what the reaction is, we'll just set up the equation in the same order. You know, even though this is a precipitation, we're going to write it backwards because that's how we're going to write all the problems. It's be backwards for precipitation, the right way for solubility. And then we'll plug in our initial concentrations here. The initial concentration will be this for the silver ion here, and this for the chloride ion here. Okay, then we have two options here. Option is just leave it as is, right? If we leave it as is, then it's a minus x, right? Or we could reset it. If we reset it, then it's going to be plus s, right? And so what should we do? Should we leave it as is or reset it? In the previous example, we reset it because that's going to make the math easier. But in this example, I might hesitate about resetting it, right? Because, well, we still know it's got to be, I don't know. I hesitate to reset it because we don't know what those values are, and which one is going to be the limiting, which one's going to be the excess, that kind of stuff. Whereas if we just leave it as is, then it's easy because here, if we do a minus x, then x is the amount that's precipitated. And if I want to precipitate out 99.9%, then that means I'm going to lose, if this is 1, I'm going to lose 0.999 of the original silver ion concentration. And so at the end of this, at equilibrium, I should be left over with 0.1% of my initial silver ion concentration. And so in this particular problem here, it might be easier not to reset it, right? In this case. Because here, you can see it's just going to be the amount that's precipitated. And so this is going to be minus the same thing because it's a 1-to-1 mole ratio. And so at equilibrium for the chloride, I'm going to get the chloride initial minus 0.999 of my silver initial here. Okay, and then what? Well, we could figure out what these concentrations must be because K is going to dictate the equilibrium concentration. And so the KSP is going to equal the silver ion concentration at equilibrium. The silver ion concentration at equilibrium is going to be 0.001 times the silver plus initial, okay, times the chloride ion concentration at equilibrium. The chloride ion concentration at equilibrium is going to equal the chloride initial minus 0.999 of the silver ion initial. Then what we'll do is we'll just substitute these in here. And then solve for Z. This would be more of a challenge problem. And solving for Z is not necessarily easy. Yeah. All right, and so in this particular case, I decided not to reset. Well, I could try to reset and then figure it out, from there. But resetting, you know, we're looking at percent remaining is a little bit more convoluted. So you have to think a little bit more and work it out. But it's not hard because it comes out the same. Well, it is actually a little hard. Well, what we can do with the common ion is we can control solubility. In fact, the more common ion we have, the lower the solubility. And one of the applications that we have, let's say, so if we increase the common ion, we're going to decrease the solubility. Even though this might not look like it, this gives us a way to control solubility. And so let's look at one application of controlling this solubility, and that's called fractional precipitation. If there's a difference in solubility, so, for example, if I had a mixture like this, and this mixture contained chloride and bromide, and then I add silver ion to this. Here. Then the silver chloride can precipitate and silver bromide can precipitate. But they don't have the same solubility. And so if I look at the KSP for silver chloride, which is 1.8 times 10 to the minus 10, and then compare that to the KSP for silver bromide. Silver bromide has a KSP of, let me get that up here. 5.0 times 10 to the minus 13, 5.0, 10 to the minus 13. You're going to see that silver bromide has a smaller KSP value. And so we have to think, in terms of solubility in pure water, which one is more soluble? AgCl, it has a bigger KSP so we can get more ions. But we have to be careful because if it's not in pure water, that is, if there's common ion present, then that can alter the solubility. And it depends on how much common ion is present. And so if this were 0 and 0, then yeah, there's going to be more silver chloride dissolving. But if this wasn't 0 and 0, then we have to think about how that impacts it. And so let's say if this were 0.100 molar, and this were 0.100 molar, so I have some common ion there to begin with, 0.100, 0.100, then it turns out, well, the solubilities are going to be the same because these are going to have the same impact, right? And so it's going to turn out that chloride will be more soluble, silver chloride will be more soluble than silver bromide. But if I change this and make this like this, if I make this 0.500 molar and the bromide 0.000500 molar, and then is the chloride, silver chloride, still more soluble than the silver bromide? And so we have to think of the multiple factors influencing solubility. So in pure water, all we're looking at is this. Silver chloride solid, this is going to go to silver ions and chloride ions. And so we start off in pure water, we assume nothing's dissolved. And then this is going to be plus S, this is going to be plus S, and so we're going to end up with S molar and S molar. And so the KSP is equal to S squared. In other words, S is equal to the square root of KSP. If we look at silver bromide, it's the same thing. You know, silver bromide, solid, this is going to go to silver ions plus bromide ions. And we start off in pure water, it's 0, 0, change, S, S. And we get the same thing, you know, S is equal to the square root of KSP. But all of a sudden, if we start putting common ion in there, common ion is going to change its solubility. So for example, if we start off with 0.100 molar chloride and 0.100 molar bromide, then the solubility is going to go down, right? The solubility goes down because now all of a sudden the solubility is not dependent on this. As I originally written, the solubility is going to be slightly different. The solubility now is going to be S times 0.100 plus S. And the solubility is going to actually have been decreased. But it turns out it's going to impact both of these the same, right? Versus if I did this, let's say I had PbCl2. PbCl2 is going to go to Pb2 plus 2 chlorides. If I have 0.100 molar chloride there to begin with, as common ion, then it's going to have a different impact because in this case the solubility is going to be plus S plus 2S here. And so at equilibrium I'm going to have S and then 0.100 plus 2S. And so this is a slightly different equation, which means the solubility impact is going to be different. But these two are going to yield the same equation. That means the solubility impact is going to be the same for both of these, right? That this one will be different. And so when we're talking about solubility, solubility is tricky because you can't just look at the KSP, right? The magnitude of the KSP, normally if we look at an acid, you know, which one is a stronger acid? We look at the Ka. The bigger the Ka, the stronger the acid. The bigger the Kb, the stronger the base. It's simple, right? But for KSP, it's not exactly the same because, you know, the bigger the KSP, the more soluble you predict, but it's complicated. It's complicated because of how it splits and the common ion effect. And so, you know, when it's even like this, we have to be careful. If it's even like this and it splits the same way, then we can make a direct comparison. But if it's even like this, that is, we have the same amount of common ion, but it splits differently, then the impact on the solubility is actually different. And so, you know, sometimes we can just look at the KSP and say, okay, like in pure water, this is easy. This is going to be more soluble, right? But when I all of a sudden I throw in something else that splits up differently, then I have to worry, you know? Just because it has a different KSP doesn't necessarily mean it's going to be more or less soluble because of how it splits up. And so we can take a look at something like, let's take a look at, magnesium phosphate. So if we look at the KSP of magnesium phosphate, which would be Mg3PO42, KSP is 1 times 10 to the minus 25. You might say this. You might say the most soluble would be silver chloride because that has the highest KSP. It's going to get the most ions in solution. The least soluble should be magnesium phosphate because it has a very small KSP, so very little dissolves, right? But the problem is we have to look at how magnesium phosphate solubility relates to KSP. In this case, in pure water, the KSP is just equal to the solubility squared. But in pure water for magnesium phosphate, it's a bit more tricky because in pure water, this splits up into 3 magnesiums and 2 phosphates. And so in pure water, nothing's dissolved, and then let's go ahead and let it equilibrate. So this is going to be plus 3s, this is going to be plus 2s. And so we're going to get 3s molar here and 2s molar here at equilibrium. And so the KSP here is going to equal the magnesium concentration cubed times the phosphate ion concentration squared. And so this is going to be 3s quantity cubed, 2s quantity squared. And so this is 3 times 3 cubed would be 27 times 4 is 108 s to the 5th. And so now all of a sudden, when we look at s, it's a much more complex relationship, than in silver bromide and silver chloride. And so whenever we're asked the solubility, we have to consider a number of factors. We just don't look at the KSP. And so if I have something like this, in pure water, chloride's more soluble. In 0.100 molar chloride and 0.100 molar bromide, then silver chloride is still more soluble. But when I change it, now I'm going to add another factor, and the other factor is it depends on how much common ion I have. The more common ion I have, the lower the solubility. And so we said that silver chloride is more soluble because it has a bigger KSP. But when you look at it, well, if I have 0.500 molar chloride versus 0.000500 molar bromide, which one is more soluble? Now that becomes a tricky question. It becomes a tricky question because I have much more common ion for chloride than I have for bromide. If I have more common ion for chloride, that means its solubility goes down. And so the only way we're going to be able to solve something like this is by doing a calculation. We'd have to actually calculate the solubility. In order to calculate the solubility for something like that, this is what we do. The solubility changes depending on how much common ion. So here, we're starting off with 0 silver, so we're assuming nothing dissolved, but 0.500 molar chloride. And so the change is going to be plus s molar, and so at equilibrium I'm going to get s molar and 0.500 plus s molar. KSP is equal to 1.8 times 10 to the minus 10. And so this is going to equal s times 0.500 plus s. We're going to try the simplifying assumption. S shouldn't be so big because K is kind of small. We got significant concentration to begin with, so this should be S times 0.500, which is going to be half of that. And so the solubility is going to be 0.9 times 10 to the minus 10 molar superchloride. When we do silver bromide, which has this much smaller KSP value, silver bromide is orders of magnitude smaller. So we got 0 here, and then 500 molar common ion here. And so it's going to be plus S, and then 500 plus S. And so the KSP for this is 5.0 times 10 to the minus 13, which is quite a bit smaller than that. But this is going to equal S times 500 plus S. Even though this is a small initial, we'll just try the simplifying assumption, see if it works or it doesn't. Here, the simplifying assumption is no problem. The change was minimal compared to the original. You got a different S?
Yeah, 3.6.
For which one? This one?
Yeah.
Oops. All right. What did you get?
3.6 times 10 to the negative 10.
3.6 times 10 to the negative 10? Okay, yeah, you know what, I did it backwards. 3.6 times 10 to the negative 10. Thanks. Yeah, I divided by half, I multiplied by halves. 3.6 times 10 to the negative 10. Here we use the simplifying assumption, and we end up with an S value of what?